So the thing worth mentioning is maybe how does varying this hyperparameter of the SVM fits to the language we used last week in controlling variance and bias. You can view it like this. If you vary the C parameter, this basically controls how fat your margin can be. If you have a bigger C, a bigger penalty for misclassification, this will result in fewer vectors being within the margin. So the margin will shrink. But it will also mean that you will have fewer support vectors. If fewer support vectors define the exact position of your classification hyperplane, this means that if these few support vectors would just slightly be differently measured, this would directly change how your classifier looks like. And this is exactly the intuitive definition of the variance part of the error. That it is very dependent on the exact data points you train on, and if you would train on slightly different data points, your classifier would look differently. So by increasing C, you decrease the margin, decrease the number of support vectors, and by this increase the variance. So this is how the language fits of what we are doing here and what we were talking theoretically about last week. Some experimental observations on how varying the misclassification penalty parameters, what effect could that have? When you work in bioinformatics, when you work on gene expression data, you usually have a very special case, special amongst all other areas of data science that I know. The special case is that you usually have more features than you have observations. I'm very much used in my personal work to the opposite. I usually have much more data points than I have features. That's a typical case, for example, when you're in speech processing, when you're in multimedia analysis, even image analysis. You usually have more instances of features. In gene expression data, it's the opposite. You maybe have a couple of hundreds data points, but all of them have thousands of features. That's a very special case, and usually your data is, because of that, always somehow separable. Because you have so many dimensions, you have much more dimensions than you have data points. What you usually do there in order to find out which value when you build a classifier of C works well, you plot your misclassification rate versus the log of your C parameter. This also tells you something in which increments should I increase the C. Does it make sense always to say +1 or +10? Or do you have to multiply it or even increase it exponentially? Yes?
What would happen if you take C and you make a range with maybe 10 steps, and then you make the border, and then you take the thought results for each C and combine them to a new one?
You want to build an ensemble?
Yeah, with multiple C. Do you actually get information out of it, or is it still?
I've never seen it that you take the support vector machines built with different C's and then build an ensemble out of that. Usually there you have a clear optimum. Like you start with a low C, you increase it until the result looks reasonable, and then you stop increasing it and take where it's reasonable. And you can actually see that very well if you do something like that. If you do a systematic analysis of starting with a low C, here it's 10 to the power of -9, and then increase it by 1 or 2 orders of magnitude in each iteration. And you basically see, oh, here the error comes down and it doesn't come down anymore. Then you don't increase the penalty factor anymore. This seems to be a good point here. It doesn't make sense to take all these classifiers and these classifiers and throw them into an ensemble. Basically, if you go back to this thing, this classifier has learned something reasonable. This as well. This arguably is exactly the same. This, I'm not so sure anymore if the position is reasonable, but if you go back further, this classifier is not reasonable at all. So you don't want to have it in an ensemble. Does it answer the question? Okay. Take-home message here is, if your task is to fit a classifier to some set of data, you have to systematically, you have to fiddle around with a hyperparameter, and I would strongly suggest that you do that in a systematic way. You define an upper and a lower limit, and you say, okay, I want to have 10 measurements within that, and then you sample that space, you do a grid search basically, and systematically evaluate what works.
If you have too big data to play with the C because it would take too much computing time, it's a good idea to lower your data set to less points and try it there and then try with the same C in a bigger set, or is this not a good idea?
Question is, what do you do if you have to train multiple times because you have to fiddle around with the C, and this takes too much compute for your capabilities, or even
Yes.
can you do? Yes, of course you can downsample your data set and just train on a sample to get an idea what range of C would be good. Probably I would do that. I would downsample a bit so that it's feasible, and try the whole range and then see where is the sweet spot. I mean, if this plot looks something like, so you have here somehow your error, and here you have your log C. And if that thing somehow looks like this, then I would take this area and redo the experiment with a larger data set probably. If it looks like this, maybe you should go even smaller. If it looks like this, maybe there's a different problem in your data. Yeah, so subsampling can be something you can do. You should always do it very randomly. Make sure you do it randomly, not just take the first 20% of rows in your CSV file or something like this. And as soon as you have something like that in your setup, you should probably try it 1 or 2 times with different random things and see if the results are consistent. And usually, I'm not a huge fan of subsampling. So better go to your project manager and ask for more compute. I mean, usually compute is so super cheap compared to your working time. It almost always makes absolutely no sense to think strongly about computational efficiency when you just can add more compute and do it so super. It just doesn't make sense under every possible measure. It doesn't make sense. If you can solve it with compute and it's somewhere available, make sure you get it. Good. Kernels. Now this stuff starts becoming really useful. We talked about the maximum margin hyperplane classifier that for linearly separable data finds the one with the fattest margin, the biggest prospect for generalization. Then we introduced the idea of, okay, data is not linearly separable, we have the budget for misclassification, or vice versa, the penalty from misclassification. And how can we deal with that and still find a classifier with a big margin? That is where we are. Now we want to talk about data that is not linearly separable. And now we are finally at the support vector machine. I once heard it say amongst several researchers that the origin of the term is probably due to a misnomer. It dates back to Vladimir Vapnik, and what I heard and cannot confirm, but I heard as an anecdote, is he intended to say support vector algorithm, and because algorithm, because he translated it from the Russian language, somehow algorithm and machine is close together, and it came out as machine. But what is meant is support vector algorithm. It's not about an embedded machine or somehow coupling with hardware. It's about a computational method. But anyway, it's famous for under the name support vector machine, and this is the third development step in the 3-step development idea we looked at today. What was missing yet? train a classifier for linearly not separable data. So the support vector machine can deal with any kind of data, linearly separable or not. Here we have such a data set. We have the red dots and the green how do you call that? Squares. They are separable, but they are not linearly separable. So a hyperplane classifier doesn't help. Right? We would need something non-linearly. The problem is, the opportunity is, we now have a very, very nice method that can build a hyperplane classifier as long as the data is somehow linearly separable. And we want to make use of it. Why? Because the support vector classifier has very strong theoretical properties that make it very nice to deal with. For example, support vector machines usually have no problem with high dimensionality in the data. There are lots of classifiers that suffer hard from the so-called curse of dimensionality. You will hear about it, I think, a little bit next week. No, in 2 weeks. Many classifiers suffer from it. As soon as your features exceed more than 10 dimensions, you can basically throw the method away, don't look at it. Support vector machines can easily deal with a couple of hundreds of dimensions, even thousands, no problem. So it has nice properties and it's computationally very efficient. And as soon as it's trained, the model is very compact. So it has nice properties. It would be nice to make use of it and just extend it to this case. If it makes sense to train a non-linear classifier, it's a whole different story. I have it on the slides here because I used to co-teach that course together with a colleague who has his most of his practical experience in gene expression data. The thing we talked about the slide before, where you have much more features than observations. In such a case, it's basically your death if you take a nonlinear classifier, because you can fit basically any function to that. It will always find a nonlinear separation that has nothing to do with patterns in the data. So in that case where you have much more features than observations, the only thing where you can find out something is to take a linear classifier, so a very simple classifier, and constrain it a lot to not have too much misclassifications and see if that finds something interesting in the data. If you train something non-linear, it will work almost perfectly on any training set and almost not at all generalized to any unseen data. Because you have no grounds in your data to train a more complicated algorithm that can separate the data non-linear. So nonlinear classifiers are somehow much more complex. They can fit much more tightly to the data, and there's a much higher chance to overfit. So you need to back up the assumption of I need a nonlinear classifier by much more observations. And in gene expression data, you don't have them, so there it's basically a deadly sin to use a nonlinear SVM. The field of science where I come from, multimedia analysis, there you have absolutely no chance at all to start with anything linear. You can just forget about it. You don't even have to think about it. You need a nonlinear classifier because all the patterns in the data are nonlinear. So for me, as coming from multimedia analysis, I never thought about linear support vector machines. That's okay. I don't care. Where's the nonlinear stuff I need? So it depends a little bit on what your application is, what your field of study is, where you want to use it, if it makes sense to use a linear or non-linear SVM. Just a remark. So we will now look into how can we actually apply our linear hyperplane classifier to such a problem. The problem is solved in a remarkably simple way. Think about this data set. 2 classes, 3 instances, we have the blue and the red stars. The data is one-dimensional, we want to separate it by hyperplane. And this is, of course, impossible. We cannot put a hyperplane here. It will not separate it perfectly. We cannot put it here, not here, not here. We will always have a blue star on the wrong side. At least one blue star on the wrong side. How can we solve the problem? We could increase automatically the dimensionality of the data. I mean, of course, we could measure something else and add another feature, but that's usually not a thing you can do. Ask your data engineers to just get more data and measure something else. We're talking about something automatically. What are we doing here? We're adding to the one dimension here a second automatical dimension that is just the square of the original data point. Now our data is two-dimensional. And of course, because it's x and x squared, they're all oriented on a parabol. And points on a parabol you can easily separate linearly. So the whole idea in support vector machines, how you can make use of the optimal hyperplane classifier and still apply it to nonlinear separable data is we project our data into a higher dimensional space, and in that higher dimensional space we assume that the data is linearly separable, or at least with some misclassifications as we saw in the case of the support vector classifier, not yet support vector machine. So the only thing we add to the support vector classifier in order to arrive at a support vector machine is to add this scaling up to a higher dimensional space in which we assume the data will be linearly separable. That's the idea. How can we do that automatically? For example, we can add the square features. Or we could add any degree of polynomial features. And at some point, by adding features, you will arrive at a space where the data is linearly separable. It's just a question of it makes sense, but it's always possible. The interesting thing becomes, we are now talking about two different spaces. We have the input space in which the original data lives, the axes live in our input space. This is the data that we collected, that is in our CSV file or in our database hopefully, or whatever. That's our training data. Now we automatically construct additional features, and by this we project our input space into a high dimensional space, the so-called feature space. In this specific case here, where we add just the quadratic feature, this feature space is quadratic. Input space is still linear. We can now fit a linear function in feature space that can linearly separate the data in feature space that is not linearly separable in input space. That's the whole idea. Quite a simple idea. And now we can start extending it. We somehow have to, let's try to explain it like that. We somehow have to give that feature space transformation a name. We have to define a function that, given an instance from our data set, creates an instance in the projected higher dimensional space. We need some function if we do that. Think about you would program it. You would do it with some function, you would give it a name. This function we usually call the kernel function. Do we have the word somewhere? Yeah, we have it here. So in the case we saw on the last slide, where we blew up the input space from just x's to x and x squared, we could formulate it this way, and we can formulate it as some kernel function, k of two instances of x. For what do I need them? I need them here. You remember that equation, the upper one? This is from one of the earlier slides where we very quickly talked about how is the support vector machine trained, with which method is it optimized, and this was a so-called dual form that is input to the Lagrange multiplier optimization procedure. And you maybe remember that we quickly talked about that the features do not enter as is into the classifier, into the optimization. They just enter as a scalar product, as an inner product. You remember? So the features just enter as an inner product. What we could now do, we could rewrite that as Same equation, everything completely equal. We just add the k function, and the k function cares for what do we actually do with these two feature vectors. Do we just build a scalar product out of them? Or do we first blow up the space, like transform them to a higher dimensional space, and then perform the scalar product? The interesting thing is, computationally, that this can be pre-computed. You could think of, when you have the curse of dimensionality in mind, ooh, I already have, I don't know, 100 dimensional features. Now I want to add squares for everything, so I would have 200 dimensional features. If I do not just want to add squares, but all polynomial degrees up to 10, I would have 10 times as many features. That's a big problem, even computationally. It's not a big problem, because you just have to compute the kernel once, can store the result, the scalar that comes out of it, and plug it into the equation. You can do that before any optimization starts, and that makes it very computationally efficient. So, in the context of support vector machines and kernel methods, you very often hear about the so-called kernel trick. This is the kernel trick. That instead of just computing the inner product between your original input space features here, you can use a function that is computing the inner product. And this function could also do a projection into a higher dimensional space. And this actually doesn't matter, because in the end, what enters the optimization is just the scalar that results from the function. So it's actually not more costly to go to a much higher dimensional space and do the separability thing there and the optimization. It doesn't cost you anything. Just a scalar enters. You have to do it only once. Nice. So, when we formulate it like this, like with a kernel function, and we have seen one specific instance of a kernel, no, we have seen two specific instances of a kernel function here. Just computing the inner product of the input feature vectors and adding the squared features. You can of course think of much more possible kernel functions. And actually, this is something that research did for a couple of years around the year 2000. Starting a couple of years before the year 2000, extending, I would say, up to 2005 maybe, 2006. People did a lot of research into, okay, what can I do with this fundamental idea of building a classifier that is actually linear, but before that, I transform my data into a high-dimensional space. With what function could I transform it, and for what kind of data, what kind of problems does it work? Actually, in that time, you got a paper published if you wrote using support vector machines to do blah blah. That was enough novelty for a year or two. That somehow reminds me remarkably of what you can do today with using CNNs to do whatever you could do in the last 2 years. It starts becoming more difficult. So that was really the deep learning of the time then. It was quite a hype. And people started to experiment with these kernels. They even came up with kernels for data that is not just in any vector form. For example, for strings, to do machine learning on texts with support vector machines. There's a great book by Christianini and Shoei Taylor that basically summarizes this line of research and give a very good introduction of what has been done there, what can you do with it. And because support vector machines are a really good out-of-the-box method, it actually makes sense today to know the method to some detail and know where you can apply it. So, there are hundreds of thousands of different kernels probably. People wrote their PhD dissertations on defining kernels for specific problems. Besides that, there are a couple of kernels that are of general interest. The identity kernel is just the inner product. That is the thing we talked about all the first part of the lecture. The polynomial kernel is a very helpful one as well. You basically get another hyperparameter, the parameter d, the degree of the polynomial, and then automatically features up to the polynomial degree d will be added to your feature vector. So if d is 2, you will have your x's, the different dimensions of x, plus a different dimension of the same thing squared. If If it is 3, you will have it to the power of 3 as well. So you can go to a degree d polynomial. And d, of course, is up a hyperparameter. You have to experiment with it, which one works best. Another very famous thing, actually the thing that is probably most used in practice when you want to use a nonlinear SVM, is a so-called radial basis function kernel, well known under this name, the Gaussian kernel. What the Gaussian kernel basically does is it places a Gaussian curve, a Gaussian kernel. You can basically imagine it like a, yeah, of course you know the Glockenkurven thing, the bell-shaped curve, the Gaussian curve. If you imagine that in 3D, it somehow looks like a glass upside down, like a cylinder, kegel shape. You put this thing over every possible support vector, and you calculate the distance only with these other data points that are within the bell shape of the kernel. So the bell shape, it rapidly drops to 0. It's not actually 0, but so close to 0 that actually the distance to points that are outside of the bell shape don't play any role. They don't enter the optimization. So by varying the width of that Gaussian kernel, you have another parameter that gives you control over how well your method can fit to your data. And this parameter in support vector machines is called gamma. The gamma parameter corresponds to the width of the Gaussian kernels you use. If it is very wide, basically you can compare every data point with every other and compute distances, and this enters this equation here. If you make it very narrow, only data points very close to each other contribute to the orientation of your classification. And that's very interesting. So we will have a more in-depth look in how this parameter works. A little bit similarly to the C parameter, where we have the C parameter that is exposed on the user interface of the API of respective machine learning packages. And then when you theoretically think about it, we are not so much talking about C, but about that C tilde. We have here the gamma parameter that actually enters the equation, that is theoretically motivated as the width of the curve. And we have the parameter that is actually exposed in traditional APIs, which is sigma. And they are, again, anti-proportionally related. The sigma is exactly what you think in the context of a Gaussian function. It's the standard deviation. And this is anti-proportionally related to the gamma that you have in vectors. So what you actually have to define is a sigma, corresponding to the C's that we saw before. How does it look like when we vary the gamma parameter? Yeah, the sigma parameter. Sigma is exposed in the API. We have the same kind of plot we had before. We have the two-dimensional data, green and red. The ones with the blue circle around them are the support vectors. White is basically where the decision surface lies. Gray and black is the margin, and the red and green areas here at the moment are the areas where points are classified as either red or green. We start with quite a small sigma and a reasonably high C value. So at the moment we assume the C is fine here, and we want to vary the sigma. And as you will see, the sigma somehow corresponds to how nonlinear is the decision surface. So while with the C, you basically say how many misclassifications are okay during training that control the width of your margin, the C says how nonlinear is my decision surface. If you increase it a lot, it will become linear again, or almost linear. If you make it very, very small, you have this very tiny Gaussian kernels, which basically means you have a very nonlinear, highly nonlinear decision surface. that is basically almost instance-based classification, where only points that are very close to a support vector actually have a chance of being classified. So, because here in that plot we don't see much with a small sigma, this is a zoom of that area here. So we see a little bit better. You see white, the decision surface, black, gray where the margin is, and the red and green areas where points are classified as red or green. And now we start increasing sigma. So you see already, when we increase it a little bit, that the decision surface will smooth out a little bit. And we just doubled it here. Now we don't need that anymore because we can see it here. Now it looks already similar to how the linear support vector classifier looked like, right? So by increasing and decreasing the sigma, you can have really a smooth control over the degree of nonlinearity you want to allow. So we can increase it quite a lot still, and at some point the same happens as with the linear classifier, that the thing will completely disregard the data. What have we seen up to here? We've seen the 3 steps going from the maximum margin classifier all the way to non-linearly separable data with the use of the kernel trick and kernel functions. And we've seen one particular nonlinear kernel that is interesting for general purpose applications. The Gaussian kernel, in which you have another hyperparameter. In addition to the C, you have the gamma. It's anti-proportional thing, the sigma parameter. With sigma, you control the degree of nonlinearity. The more sigma, the less nonlinearity, the more linear it is. The smaller sigma is, the more nonlinear the stuff is. Corresponding to C, the higher C is, the smaller are the margins. So now we have 2 hyperparameters that you can tune.
How do we know which margin correspond to which color or which label? If you go back to the sigma with much non-linearity, we don't know which, if they are in the gray space, the points, which color, which label they will take.
I think it's difficult to see from the plots. For the method, this is there will be a unique decision, but it will not make much sense. You see from the points basically that such a low value of sigma doesn't make much sense. Exactly the same way as you saw before that a very low value of the C parameter doesn't make much sense in that particular example.
But even if you go to a higher sigma, there you have a lot of white space outside. How can we find out which label it is?
I interpret it this way, that this basically surrounds the green class. So everything within this side of the margin is green, and everything on the other side is red. And you can now, but admittedly it doesn't come through very nice on these plots. And in higher dimensional spaces, when you have more than 2 input features, it's anyway not a good idea to just look at plots. You have to look at basically how accurate is it on the test. Okay? There's just one thing missing for today that we need to do is, and this is, we have to talk about how can we extend the support vector machine from a binary classification case to multi-class case. We will do that in the remaining, I think, 2 slides, so not too much material left. Just as a note, support vector machine, I told you, is an approach that has been heavily used and also heavily extended to be applicable for almost every possible use case in machine learning. So we looked at classification today. You can use support vector machines also to do regression. There's a support vector regression model that is usually part of every support vector machine library you can have. So you can use a method for regressing to numerical values. And there's also a variation called the one-class support vector machine, where you can use it for anomaly detection. There's a slide in the appendix that basically shows how it looks like. It comes down to you just give it data, and you have another parameter where you control how much of the data should be part of the model and the rest classified as outliers. And out of this data plus this parameter that tells how much is in, how much is out, it will construct the best possible, say, contour of your data that contains the most probable data points. If you tell it 20% shall be modeled as outliers, it will model the 80% most probable data points as belonging to the one class you want to model. That's a very good model if you want to do anomaly detection in any possible way. But here we're talked about binary classification, and we will now quickly extend it to the multiclass case in a very general way. So if you have a method, a nice method that does binary classification, how can you extend it? Quite straightforward way is so-called one versus rest scheme. What are you doing there? When you have three classes, you're training three different classifiers. Always one class versus all the others. So here it's red versus the rest, blue versus the rest, green versus rest. Generally, you have number of classes times this class versus the rest classifier. If you have this, what you do is you basically build an implicit ensemble. You get a new data point, for example this. You have only three classifiers built based on your training data. And now you want to know this instance, what class does it belong to? What you basically do, you compute the distance of that point to any hyperplane from the different classifiers. So here, let's say this is -3. Let's say this is -2. It's a little bit closer to the hyperplane, but it's still on the wrong side for being classified as blue. And here, it has a positive distance, so it is basically on the side of the one versus rest class. So in that case, generally you take as classification the result of the classifier with the highest positive distance. So in that case, this point would be classified as green. That's a possible scheme you could do, and of course this is not particular for SVMs. You can use it for any binary classifier you want to extend. But similarly, naturally, this is not the only way you could do it. Different scheme would be the one versus one classification, where you need to build much more classifiers. In fact, you have to build k times k minus 1 over 2 classifiers, where you always build, where is it? You build the pairwise comparisons of every class with every other class. And what you then do is a majority vote amongst all classifiers. Like in the one versus rest scheme, you basically take the maximum positive distance and say, this is it. Here you take a majority vote. Question arises, which method is better? And as often, there are criteria to decide, but it's not per se that one's better than the other. It depends a little bit on what you want. And what I think is very helpful are these two pictures to explain it. The one versus all method, this is the one from the previous slide, builds less classifiers. So it has less training time. That's a computational advantage. But it has smaller margins. Because actually what you're doing, you're giving up some information that is in the data you don't use anymore. When you're building this classifier here, the green versus rest, you're giving up the information that blue and red are separate things in your training set. And this giving up of information, not making use of information that you would actually have, gains you computational time. It's not so costly than other methods, but it costs you margin. It costs you generalization performance. On the other hand, if you build a one versus one classifier, That's computationally more costly. In general, when you have more than 3 classes, you have to build more classifiers, but they will have a fatter margin. Because to build this line, you just have to regard the orange and the blue. Green plays no role here. That creates a larger margin between these two, and the same for all the others. That suggests that if you have time, and if you have to think about it, and if you have compute, you might favor the 1 versus 1. Usually, you actually don't have to think much about it because SVM libraries give you a default implementation for multi-class classification. You're not even asked. It will just use whatever is implemented. And you can basically rely on that this is a quite good choice for almost all cases. That concludes what I wanted to tell you about support vector machines. The interesting thing is the feature space transformation and the kernel trick. The feature space transformation is interesting because it makes non-linearly separable data linearly separable in higher dimensional space. And the kernel trick is that just the kernel function, the scalar value that comes out of it, enters the optimization, is a guarantee for that this is computationally feasible. Interesting fun fact, if you use the d-dimensional polynomial kernel, this will project your data into a d times higher dimensional space, right? So if you have the d equals 2, the quadratic polynomial space, your space will be 2 times more higher dimensional. If you project into using the Gaussian kernel, you have no parameter that tells you how high dimensional is a space now. But you can theoretically show that the space you project your data into using the Gaussian kernel is infinitely dimensional. Yes. It's infinitely dimensional. I don't know how you come up with this and how you prove this, but apparently it has been proven. So you transform your features implicitly into an infinitely dimensional space in order to do a linear separation there and find the best possible linear separation there. That sounds quite powerful, and actually it is. If you have data for which a nonlinear classifier makes sense, the Gaussian kernel is actually quite a good idea. And maybe it is related to that. This is an implicitly infinitely dimensional space. Anyway, in the end you have 2 hyperparameters that you have to care for and that you have to tune as a machine learning engine. The C, and in case of the Gaussian kernel, the gamma. So with the introduction of this algorithm, and probably for you not for the first time, you will have to, as part of your routine of training this kind of methods, you have to do hyperparameter optimization. You have to think about systematic experimentation to do this. And actually, this is what the what the lab for today includes. It's the task 2 from the V04 lab. It's again a Jupyter notebook. I think we introduced it last week already to give you some hands-on experience with this interactive Python stuff. The idea is here to play around. You don't have to code anything. Like the code is already there, already once. The idea is read it, understand it, and then play around with it. Especially play around with the parameters. The C, with the gamma, or sigma it's probably called here. Play around with it and see, get a feeling for in which range do I sample values, what makes sense, how can I arrive at a good solution. Try it for yourself, compare with your neighbor, have fun, and see you later or next week. Yeah, last question.
I have a more general question. We heard now this support vector machine is almost in every scenario a very good approach. Does history show that in certain programs the support vector machine does not work very well?
Nowadays, I wouldn't at all try it for any image classification problem. Or any other problem where your input is quite high-dimensional sensory input. Why? Because for the support vector machine, you need good features. So you have to rely on the feature engineering of whoever did it. If you have that, if you have very good hand-engineered features, support vector machine is a great classifier. But if you have raw data and you actually don't know what makes up good features, and your input is such that it makes sense to, or it's possible to learn the features automatically, I would always use a deep learning approach. So if you have images and you're not sure it's exactly that feature that I have to extract and feed to the SVM, I would use a deep learning method. If you have good features, support vector machine is a thing to try. And even what I see nowadays more and more is that people use a deep learning approach to extract some embeddings, like the activations of some upper layer in the neural network, extract them. These are usually quite high dimensional, between, I don't know, 500 and 2000 dimensions or so. And support vector machine can deal very well with it. And you can train a support vector machine on top of the deep learning features. That's done quite often, actually. For example, when you have image classification problems like face recognition, and you only have very, very few instances to recognize a certain person. Like, let's say you want to give access to some room and you only have 2 or 3 training images per person that has to enter that room. That's not a good idea to train end-to-end a deep learning system that classifies has access or has no access. But you can take a very general face recognition deep learning system to extract facial features from an image, feed them to a support vector machine that you can train with just 3 or 5 or so images, and say with quite high confidence this is a person or not. Does it help? It's definitely one of the things you should have in your toolbox as a very good out-of-the-box method that is computationally efficient, has nice properties, not prone to the curse of dimensionality, easy to handle, not many hyperparameters. Good thing to have in your box, and good thing to have some practical experience with. More such questions? See you later or next week.